What if the brightest things in the universe are not stars at all? What if the most powerful light we can see does not come from burning fuel, but from something that never shines on its own? Somewhere in the sky, there is a point so small it barely stands out, yet it releases more energy than entire galaxies combined. Its light began traveling long before Earth existed, crossing an expanding universe without sound or intention. Why the universe allows such a small region to become so overwhelmingly powerful? Tonight, we begin with that question. When people first hear about quasars, they rarely imagine that the problem lies not in complexity, but in familiarity. The misunderstanding does not come from knowing too little about the universe, but from knowing just enough to be confidently wrong. For most of human history, light was simple. Something glowed because it burned. A fire burned because it consumed fuel. The sun burned because it was hot. Stars burned because they were larger, hotter versions of the same idea. This mental model, shaped by everyday experience, worked well enough to build calendars, navigate oceans, and eventually construct physics itself. Even when nuclear fusion replaced fire as the explanation for stellar energy, the deeper assumption remained untouched. Brightness comes from things that are actively burning. This assumption is so deeply embedded that we rarely notice it. When we see something bright, we instinctively look for heat, for fuel, for combustion. We expect light to be tied to temperature, and temperature to be tied to some internal engine that slowly runs down. Quasars violate this expectation at the most basic level. At first glance, they appear almost disappointingly ordinary. Early astronomers, peering through mid-20th century telescopes, saw them as unresolved points of light, indistinguishable from stars. They were cataloged as quasi-stellar objects, not because anyone understood what they were, but because they looked like stars and behaved like nothing else. Their spectra were strange, their distances incomprehensible, but visually, they were stubbornly unimpressive. This created the first and most persistent misunderstanding, that quasars are stars, perhaps unusual ones, perhaps very large or very hot, but still stars nonetheless. They are not. No star, no matter how massive, can sustain the energy output observed in a quasar. A star produces energy by fusing lighter elements into heavier ones in its core, converting a small fraction of mass into energy according to Einstein's equation. This process is remarkably efficient by human standards, but cosmically modest. Even the most massive stars are limited by a delicate balance between gravity pulling inward and radiation pressure pushing outward. Increase the energy output too much, and the star tears itself apart. Quasars show no such restraint. Their luminosity exceeds what nuclear fusion could plausibly support, often by orders of magnitude. If a quasar were powered by fusion alone, it would consume the equivalent mass of many suns every single year. The object would not survive long enough to be observed. Yet, quasars persist for millions, sometimes hundreds of millions of years. This leads to the second common misunderstanding, that quasars must be explosive events, brief cosmic catastrophes frozen in time by distance. They are not explosions. Explosions are sudden, chaotic, and short-lived. Quasars are structured, directional, and persistent. Their light fluctuates, sometimes dramatically, but within bounds that suggest regulation rather than collapse. The universe is full of violent events, but quasars are not among them. They are closer to engines than to bombs. Another assumption quietly fails here, that darkness is passive and light is active. We imagine black holes as sinks, as cosmic drains where energy disappears. The phrase itself, black hole, suggests absence, loss, erasure. This too is misleading. A black hole, by definition, does not emit light from within its event horizon, but the space around it can be the brightest place in the universe. The paradox is not a flaw in physics, it is a flaw in intuition. We tend to treat objects as isolated things, ignoring the environment they create. Quasars force us to abandon that habit. The black hole at the center of a quasar is not the source of light. It is the reason light exists there at all. To understand this, we must let go of the image of matter simply falling inward and vanishing. In reality, matter approaching a black hole almost never falls straight in. Space around rotating objects has angular momentum, and angular momentum resists collapse. Instead of plunging directly into darkness, gas and dust begin to orbit. flattening into a rotating structure known as an accretion disk. This disk is not a passive ring. It is a site of relentless motion. Particles in the inner regions orbit faster than those farther out, creating shear forces that tear at the disk from within. Friction converts motion into heat, and gravity ensures that the closer matter spirals inward, the more energy it must lose to move deeper into the gravitational well. The result is not quiet absorption, but intense radiation. Here lies another misunderstanding, that gravitational energy is weak compared to nuclear energy. On Earth, gravity feels gentle. We fall slowly. We climb hills without thinking about it. Gravity seems incapable of producing light. Near a supermassive black hole, gravity is anything but gentle. The conversion of gravitational potential energy into radiation in an accretion disk is astonishingly efficient. Up to 10% of the infalling mass can be converted directly into energy. For comparison, nuclear fusion converts less than 1%. In practical terms, this means that dropping matter into a black hole releases more usable energy than burning it in a star. This is not because gravity is stronger than nuclear forces in principle, but because black holes allow matter to fall much deeper into a potential well than any star ever could. There is no surface to halt the descent, no equilibrium to maintain. Matter keeps falling until physics itself forbids further observation. The brightness of a quasar, then, does not come from what the black hole destroys, but from what it nearly destroys. The light is produced in the final orbits before matter crosses the point of no return. This distinction matters because it reframes the entire phenomenon. A quasar is not a hole shining, it is a process shining. Once this is understood, another misconception begins to dissolve, that quasars are rare cosmic oddities. They are rare today, but they were once common. Observations show that quasars were far more abundant when the universe was young, particularly within the first few billion years after the Big Bang. This fact initially puzzled astronomers. If quasars require supermassive black holes, and black holes take time to grow, why were they more active earlier? The answer lies in the conditions of the early universe. Young galaxies were rich in cold gas, the raw material of both stars and accretion disks. They collided frequently, merged often, and lacked the stable structures seen in mature galaxies. Each collision disrupted orbits, drove gas toward galactic centers, and fed the central black holes at rates unimaginable today. In this environment, quasars were not exceptional. They were a natural phase of galactic adolescence. This leads to another quiet correction. Quasars are not separate objects from galaxies. They are galaxies, temporarily dominated by their central engines. When the fuel supply diminishes, the quasar fades, and the galaxy continues its existence in a quieter state. Our own galaxy bears the scars of this history. At its center lies a supermassive black hole, dormant but present. There is no quasar here now, no blinding light, no relativistic jets cutting across intergalactic space. But evidence suggests that, in the distant past, the Milky Way may have experienced a brief quasar-like phase, leaving subtle imprints in surrounding gas clouds. This realization shifts the narrative from spectacle to continuity. Quasars are not alien intrusions into cosmic order. They are expressions of it. Still, one final misunderstanding remains, perhaps the most subtle of all. That understanding a phenomenon requires reducing it to a single cause. Quasars resist this reduction. Their energy arises from gravity, but gravity alone is insufficient. Magnetic fields thread the accretion disk, shaping flows of matter and channeling energy into narrow beams. Relativistic effects alter time, light, and motion near the black hole, changing how energy is transported and observed. Radiation pressure pushes back against infalling gas, regulating the accretion rate. Feedback from jets reshapes entire galaxies, altering the very conditions that allowed the quasar to exist in the first place. No single component explains a quasar. It is an ecosystem, not a machine. And like all ecosystems, it is unstable. Quasars flicker, brighten, dim, and sometimes disappear entirely. Their activity depends on a delicate balance between supply and resistance, between gravity pulling inward and energy pushing outward. When the balance shifts, the quasar changes state. This variability, once seen as noise, is now understood as a clue, evidence of regulation rather than chaos. What science offers here is not certainty, but structure. We know quasars are powered by accretion onto supermassive black holes. We know this process can outshine galaxies. We know it was more common in the early universe. But the details, how black holes grew so massive so quickly, how feedback precisely shapes galaxy evolution, how often quasars switch on and off, remain active areas of research. This uncertainty is not a weakness, it is an honest boundary. The deeper lesson of quasars is not that the universe is violent or extreme, but that it is capable of sustaining processes far beyond everyday intuition, while remaining governed by consistent laws. Gravity does not suddenly behave differently near a black hole. It simply reveals its full potential. By correcting these misunderstandings about light, about black holes, about energy, about rarity, we prepare the mind for what comes next. Not a spectacle, but a deeper structure. Not a mystery that dissolves, but one that becomes sharper. Only now are we ready to descend further. There is a moment in every scientific explanation where progress no longer comes from adding more facts, but from removing a mistaken center. And quasars force this moment early because the human mind instinctively places the black hole at the heart of the story and refuses to let it go. The word itself carries too much gravity, both literally and emotionally. A black hole sounds like an actor, a predator, a cosmic monster doing something dramatic to the universe around it. This image is understandable, but it is wrong in a subtle and important way. A black hole, by itself, is almost perfectly inert. It does not shine, it does not roar, it does not flare or pulse or announce its presence in any active sense. Left alone, a black hole is quiet, nearly invisible, detectable only through the way it bends space and alters the motion of objects that stray too close. Many galaxies, including our own, host supermassive black holes at their centers, and yet their cores are calm, dark, and uneventful by cosmic standards. If quasars were simply black holes, the universe would be far dimmer than what we observe. The mistake lies not in associating quasars with black holes, but in assuming they are the same thing. They are not. A quasar is not an object, it is a condition. It is not a thing. It is a state that arises when a black hole is no longer alone. To see this clearly, it helps to replace the image of a creature with the image of a structure. A black hole is best understood not as an engine, but as a gravitational center, a point where space is curved so steeply that it defines how everything nearby must move. On its own, it does nothing more than exist. The drama begins only when matter enters the picture. A useful analogy is a drain. A drain sitting in an empty basin is meaningless. It has no motion, no sound, no visible effect. But introduce water, and suddenly the system comes alive. The swirling, the speed, the turbulence, the visible patterns all belong to the water, not to the drain itself. The drain merely defines where the water can go. In the same way, the black hole defines a center, but the quasar is the whirlpool that forms around it. The black hole is static. The quasar is motion. The black hole is dark. The quasar is visible. Confusing the two is like mistaking the hole in a bathtub for the spinning water around it. This distinction matters because almost everything we observe and associate with a quasar belongs to the environment surrounding the black hole, not to the black hole itself. The brightness, the variability, the apparent violence, the immense scale of activity, all arise from matter that has not yet crossed the point of no return. The black hole itself contributes no light. It simply provides the gravitational boundary condition that shapes everything else. Once this is understood, the quasar stops being a mysterious glowing object and becomes a complex, layered system, one that is constantly changing and never truly at rest. At the center of this system lies the supermassive black hole, containing millions to billions of times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. This fact alone often overwhelms intuition, because on Earth, mass and size are tightly linked. Large things are heavy, small things are light. Our brains are trained on this consistency from birth. Black holes violate it completely. A supermassive black hole can contain the mass of 1 billion suns without occupying a volume larger than the inner solar system. Another way to approach this density is to imagine compressing the mass of an entire city, every building, every road, every human being, into a grain of sand. The numbers are not exact, but the feeling is correct. Density ceases to be something you visualize and becomes something you accept reluctantly. This density is not important yet because of what it releases, but because of what it enforces. Gravity near such an object does not gently guide motion. It dictates it. Space itself becomes steep, and every path nearby bends inward. Surrounding this central mass is matter drawn from the host galaxy. Gas clouds drifting too close, stars whose orbits have been disturbed, dust that once floated harmlessly between stellar systems. None of this material falls straight in. Every particle carries sideways motion, angular momentum inherited from the galaxy itself. Gravity pulls inward, motion pulls sideways, and the result is orbit rather than collapse. Over time, countless orbits flatten into a rotating structure that wraps around the black hole like a cosmic disk. This structure is not decorative. It is the quasar. Everything we later describe as brightness or activity emerges from this region and beyond, not from the black hole at the center. This disk, and the broader environment around it, is where the system truly exists. It is thick, turbulent, and constantly rearranging itself. Matter moves at different speeds at different distances, creating internal stresses and interactions. The system never settles into a static shape. It breathes, shifts, and evolves. Importantly, this means that a quasar is not a permanent feature. It turns on when matter is supplied and fades when that supply diminishes. The black hole remains unchanged in character, but the quasar can vanish entirely. This is why two black holes of similar mass can exist in radically different states. One may anchor a blazing quasar visible across billions of light years, while another sits quietly at the center of a calm galaxy, exerting influence without spectacle. The difference lies entirely in the surroundings. This realization corrects another deep misunderstanding, that quasars are exotic anomalies, rare monsters scattered randomly through space. In reality, they are phases in galactic life. They were more common in the early universe because conditions favored them. Young galaxies were rich in gas, frequently colliding, constantly disturbed. These interactions drove matter toward galactic centers, feeding the systems that would temporarily become quasars. As the universe aged, galaxies matured. Gas was consumed by star formation or blown away. Orbits stabilized. The conditions that sustained quasars became less frequent. The black holes did not disappear, the whirlpools did. Seen this way, a quasar is not a thing to be pointed at, but a moment in time. It is a galaxy caught in the act of extreme central activity. The black hole provides the anchor, but it is not the protagonist. It does not act, it allows action. It does not shine, it permits shining. It does not change, it shapes change. This shift in perspective is essential because without it, every subsequent explanation collapses into confusion. Energy, light, jets, and feedback cannot be understood if the wrong entity is treated as the source. At this stage, restraint is important. It is tempting to rush ahead, to speak of brightness and power, to quantify what makes quasars the most luminous, sustained objects in the universe. But doing so too early obscures the deeper structure. Before we can talk about what quasars release, we must understand what they are. They are not black holes doing something extraordinary. They are systems responding to gravity under extreme conditions. They are motion constrained by curvature. They are matter caught between falling inward and moving sideways, never quite allowed to do either completely. Once the mind releases the black hole from its starring role, the picture becomes quieter and more precise. The universe does not need monsters to create wonders. It needs only simple rules applied without limit. Gravity pulls, matter resists, motion emerges, structure follows. The quasar is not a violation of cosmic order. It is a natural consequence of it, revealed only when scale and density cross thresholds that are rare today but were once common. This correction may feel subtle, but it is foundational. Without it, the quasar remains a spectacle. With it, the quasar becomes intelligible. The black hole fades into its proper role as a silent center, and the surrounding system takes its place as the true subject of the story. Only now, with the characters correctly assigned, can we move forward and begin to ask what happens when motion within this system is pushed to its limits, and why falling under the right conditions becomes something the universe cannot hide. Once the characters are placed correctly, once the black hole has stepped back into its silent role, and the surrounding system has taken center stage, attention naturally settles on a structure that appears again and again in every serious attempt to understand quasars: the accretion disk. This disk is not an accessory. It is not a side effect. It is the heart of the phenomenon, the region where ordinary matter is transformed into something capable of rivaling entire galaxies in influence. If quasars deserve to be called the most powerful sustained engines in the universe, it is because of what happens here. The first thing the accretion disk teaches us is that matter does not fall the way intuition expects. When we imagine something being pulled by gravity, we imagine a straight descent, a clean drop from one place to another. That picture is shaped by life on Earth, where friction and surfaces simplify motion, and where sideways momentum is quickly lost. Space does not work that way. Matter approaching a black hole arrives with history, with motion inherited from the galaxy it came from, and that motion cannot simply disappear. Gravity pulls inward, but momentum insists on sideways travel. The compromise is rotation, and rotation, when multiplied across vast amounts of matter, creates structure. The accretion disk forms because matter cannot choose a single direction. It is caught between falling and orbiting, never allowed to do either completely. Gas spirals inward not along straight lines, but along tightening paths, each orbit slightly smaller than the last. The disk flattens because motion becomes organized, but it never becomes calm. Every layer moves at a different speed, faster closer to the center, slower farther out. This difference is not gentle. It tears at the disk continuously, creating internal friction on scales that defy everyday analogy. Friction is usually something we associate with loss. A brake pad slows a wheel. Hands rubbing together waste motion as heat. In the accretion disk, friction does not merely dissipate energy. It unlocks it. Motion becomes heat. Heat becomes radiation. And radiation becomes influence. The disk grows hot not because something is burning, but because motion is being forced to pay its gravitational debt. Here, comparisons become unavoidable, because the conditions are so far removed from human experience that numbers alone fail. The inner regions of an accretion disk can reach temperatures hotter than the cores of nuclear reactors, environments designed explicitly to harness the most intense reactions humans can control. But even this comparison falls short, because reactors rely on rare processes that convert mass into energy inefficiently. The disk relies on something simpler and far more relentless: falling. The heat generated by friction in the disk is sufficient to strip electrons from atoms, turning gas into plasma, a state of matter where particles move freely and respond violently to magnetic fields. In this state, matter does not merely glow. It radiates across a wide range of wavelengths, from infrared to visible light to ultraviolet and beyond. The disk becomes luminous not at a single temperature, but as a gradient of conditions layered around the black hole, each region contributing its share to the overall output. What makes this truly remarkable is not the temperature itself, but the efficiency. In everyday life, friction is an enemy of efficiency. Machines lose energy to heat. Motion decays into waste. In the accretion disk, friction is the mechanism of conversion, not loss. The system is designed, by the laws of physics alone, to extract energy from motion with astonishing effectiveness. A significant fraction of the mass flowing through the disk does not survive as matter at all. It is transformed into radiation before it ever reaches the black hole. This leads to a counterintuitive realization. The accretion disk is more efficient at producing energy than the processes that power stars. Nuclear fusion, the engine of stars, converts less than 1% of mass into energy. Accretion onto a black hole can convert several times that fraction. In practical terms, this means that letting matter fall deep into a gravitational well can release more usable energy than forcing atomic nuclei to merge. The universe has discovered a way to outdo its own stars. The reason this works lies in gravity's role as a kind of universal battery. When matter is far from a massive object, it carries potential energy simply by being high in the gravitational landscape. As it falls, that potential energy must go somewhere. Near a planet, it becomes motion and then heat upon impact. Near a black hole, there is no surface to absorb the fall. Instead, energy is released gradually as matter spirals inward, orbit by orbit. shedding altitude and paying energy at every step. The deeper it falls, the more it must give up. This is why falling becomes light. The disk does not glow because it wants to, or because it is unstable, but because it has no other option. Energy cannot remain stored. It must be released. Radiation is the escape route. Every photon leaving the disk carries away a small fraction of the gravitational energy that matter has lost. Collectively, these photons add up to luminosities that overwhelm the combined output of billions of stars. At this point, the word power begins to take on a precise meaning. Power is not just brightness. It is the ability to influence surroundings, to reshape environments, to impose conditions at a distance. The accretion disk's power comes from its consistency. Unlike explosions, which release energy in brief bursts, the disk operates continuously. As long as matter is supplied, the conversion proceeds. There is no countdown, no ticking fuse, only sustained transformation. This continuity is what separates quasars from transient cosmic events. Supernovae briefly outshine galaxies, but fade quickly. Gamma-ray bursts release staggering energy, but last seconds. The accretion disk, by contrast, can shine at extreme levels for millions of years. Its power is not a flash, it is a pressure, and pressure changes systems. Radiation streaming from the disk pushes outward on surrounding matter, resisting further infall and shaping the flow of gas on galactic scales. Magnetic fields generated and amplified within the disk channel motion, align structures, and prepare pathways for energy to escape in focused forms. Even without naming those pathways yet, it is clear that the disk does not exist in isolation. Its activity reaches outward, influencing regions far beyond its immediate size. Yet, despite all this, the accretion disk remains a remarkably simple idea at its core. There is no exotic physics required to explain its existence. No speculative particles, no violations of known laws. Gravity pulls, motion resists, friction converts, radiation escapes. The most powerful sustained phenomenon in the universe arises not from complexity, but from inevitability. This simplicity is unsettling. It suggests that the universe does not reserve its greatest displays of power for rare or delicate mechanisms. Instead, it relies on the same forces that operate everywhere, allowing them to run without interruption or constraint. Where mass is sufficient and space is curved deeply enough, falling alone becomes enough. At the same time, honesty requires restraint. While the broad picture is clear, the details remain subjects of ongoing study. Turbulence within the disk, the precise behavior of magnetic fields, the way matter transitions between different states as it spirals inward, these are not fully solved problems. Models improve, simulations grow more detailed, observations sharpen constraints, but certainty remains partial. The accretion disk is understood in outline, not in every stroke. This uncertainty does not weaken the claim of power, it strengthens it. The fact that such immense influence can arise from processes we are still learning to describe fully is a reminder that the universe is not obliged to wait for our comprehension. It operates at scales where approximation is the best we can do. As the mind adjusts to this idea, a subtle shift occurs. Power stops feeling theatrical and begins to feel structural. The accretion disk does not dominate because it shouts, but because it persists. Stamma converts gravity into radiation with relentless patience. It turns mass into influence without drama. It outperforms stars not by burning hotter, but by falling deeper. And here, slowly, without fanfare, the title becomes justified. This is not merely a bright thing in the sky. It is not merely an energetic object. It is the most efficient sustained converter of matter into energy the universe has produced, operating openly, predictably, and on scales that dwarf galaxies. The accretion disk is where that truth becomes unavoidable. If the accretion disk is where power is generated, then the jets are where that power learns how to move. They are not subtle, and yet they are often misunderstood because they do not look like what we expect power to look like. When people imagine energy escaping a violent system, they imagine chaos spreading outward in all directions, a sphere of influence expanding uniformly. Quasars do not behave this way. Instead, they choose a direction, or rather, the laws governing them leave only two possible directions, and everything else is excluded. From the central region of a quasar, above and below the plane of the accretion disk, two narrow columns of matter erupt into space. They do not fan out gently, they do not diffuse. They remain remarkably straight, focused, and coherent across distances so large that the host galaxy itself becomes a minor obstruction rather than a boundary. These columns, which astronomers call jets, extend far beyond the region where stars orbit, far beyond the visible structure of the galaxy, sometimes stretching for hundreds of thousands or even millions of light years. To place that scale in context, a jet can be longer than the galaxy that created it, projecting influence into intergalactic space like a cosmic arrow. At first glance, the sight defies common sense. A galaxy, something we think of as a collection of stars and dust drifting slowly through space, suddenly appears capable of behaving like a machine, expelling matter in two opposite directions with extraordinary precision. The jets are thin compared to their length, sharply defined rather than fuzzy, and astonishingly persistent. They do not collapse under their own complexity. They do not quickly lose coherence. They hold their shape across distances that dwarf any human structure, maintaining alignment long after they have left the region that launched them. What is most unsettling is their speed. The material in these jets moves so fast that ordinary comparisons fail. It does not drift or flow in the way gas normally does. It races outward at a significant fraction of the speed of light, so fast that, from our perspective, time itself appears distorted in the regions they pass through. Without naming the mathematics yet, it is enough to say that this is motion, pushed to the limits that the universe allows matter to reach. Seen without explanation, the jets look less like natural phenomena and more like deliberate engineering. Two exhaust streams, perfectly opposed, aligned with the unseen axis of the system, steady rather than explosive, a galaxy that appears to have discovered how to aim. To understand how this happens, it helps to resist the temptation to assign intention. Nothing is choosing direction here. Direction emerges because of constraints. The accretion disk, for all its violence, has a geometry. It is flat, rotating, and organized around a central axis defined by the black hole's spin and the angular momentum of the inflowing matter. Within this geometry, there are only two paths that are not obstructed by dense, orbiting material, straight up and straight down, perpendicular to the disk's plane. Power, when it accumulates, seeks release. In the quasar, that release cannot occur sideways, because sideways motion is blocked by the disk itself. Matter there is already crowded, turbulent, and bound into orbits. The only open channels are the polar regions above and below the disk, where matter density is lower and escape is possible. These regions become natural outlets, not because they are special, but because everything else is constrained. Magnetic fields play a quiet but decisive role here. The disk is not only a whirlpool of matter, but also a generator of intense magnetic structure. As charged particles move, they drag magnetic fields with them, twisting and amplifying those fields as the disk rotates. Over time, these fields become organized along the system's axis, forming channels that guide motion rather than allowing it to spread. Once matter enters these channels, it is no longer free to wander. It is constrained, focused, and accelerated. Energy that was once distributed across the disk becomes collimated, forced into narrow streams that move outward with extraordinary persistence. The jets are not explosions. They are flows that have found the only available exit. At this point, analogy becomes useful again, not to simplify, but to anchor intuition. The jets behave like the exhaust of a reaction engine, where energy generated internally is expelled in a specific direction, producing force and influence far beyond the size of the engine itself. They also resemble a cosmic compass needle, rigidly aligned with an invisible axis, cutting through space regardless of what lies in the way. And in a more organic sense, they resemble breath, a galaxy exhaling energy it cannot keep contained, releasing pressure through the only openings it has. These comparisons are not poetic excess. They capture something essential about the nature of the jets. They are directional, sustained, and purposeful in appearance, even though no purpose exists. The universe, under the right conditions, organizes motion so effectively that it mimics design. Here, the idea of power deepens. Power is no longer just the ability to produce energy. It is the ability to impose order at a distance. A jet does not merely shine. it pushes, it heats, it compresses. As it travels through surrounding gas, it transfers momentum, reshaping its environment. Clouds collapse or disperse, temperatures rise, structures form or fail to form because of its passage. This influence extends far beyond the host galaxy. Jets can inflate enormous lobes of hot plasma in intergalactic space, regions where matter is stirred and energized long after it has left the quasar itself. In this way, a single quasar can affect volumes of space far larger than the galaxy that contains it, altering conditions on scales that challenge the idea of a galaxy as a self-contained system. It is here that the phrase "most powerful" earns its weight. The jets demonstrate that the quasar's influence is not confined to light traveling passively outward. It is active, mechanical, and directional. Energy does not simply radiate, it is delivered. The quasar becomes not just a beacon, but an agent of change. And yet, even now, restraint is necessary. The jets are not arbitrary. They are not guaranteed. Not every quasar produces them with equal strength, and not every black hole launches jets at all. Their formation depends on the precise interplay between rotation, magnetic structure, and the flow of matter. Small differences in initial conditions can lead to large differences in outcome. This sensitivity is not a flaw in our understanding. It is a feature of complex systems. The presence of jets reminds us that the universe does not express power uniformly. It concentrates it, channels it, and releases it along preferred paths. In doing so, it reveals something important about how structure emerges from simple laws. Given gravity, motion, and magnetism, direction is not an option, but an inevitability. As the mind absorbs this, the universe begins to feel less static. Galaxies are no longer islands drifting silently through space. They are dynamic systems capable of acting on their surroundings in dramatic ways. Quasars, through their jets, make this dynamism impossible to ignore. They show that under the right conditions, a galaxy can behave like a machine, converting mass into directed influence with relentless consistency. This does not mean the universe is alive in any biological sense, but it does suggest that it is operational. It runs, it processes, it responds. The jets are not decorations, they are outputs, visible signs that the system is doing work. At this stage, the picture is nearly complete. We have seen how matter organizes itself into a disk, how falling becomes light, and how that light and motion find direction. What remains is to understand what this power does over time, how it shapes the life of galaxies, and how something so extreme fits into a universe that is, on average, quiet and cold. But before moving forward, it is worth pausing on the image itself. Two narrow beams of matter, launched from the heart of a galaxy, traveling across distances that dwarf human comprehension, carrying with them the signature of the most efficient engine the universe has built. Not because it seeks dominance, but because gravity, given freedom, leaves no other outcome. The universe is not static, it is working. If the accretion disk is where power is born, then the jets are where that power reveals its true nature. Up to this point, everything about a quasar can still be misunderstood as brightness, as heat, as something that merely shines. The jets remove that ambiguity. They are not subtle. They do not hide in spectra or equations. They announce without words that something at the center of a galaxy is not only energetic, but capable of exerting control far beyond itself. Before any explanation is offered, before any physics is named, the image alone is enough to disturb intuition. From the heart of a quasar, two narrow columns of matter erupt in opposite directions, aligned with an invisible axis that cuts cleanly through the galaxy. They clearly do not belong to the slow, drifting structures we associate with cosmic systems. They are straight where galaxies are curved. They are focused where gas clouds are diffuse. They are disciplined where stars wander. Each column stretches outward far beyond the bright disk at the center, piercing through the host galaxy and continuing into the space between galaxies, sometimes for distances longer than the galaxy itself. Seen at full scale, the galaxy becomes a small, crowded knot in the middle of two vast beams, as if the entire system exists merely to launch them. These columns are not static structures. They are streams of matter in motion, racing outward at speeds so extreme that ordinary language struggles to contain them. They do not drift. They do not slowly expand. They surge, carrying material away from the galactic core at velocities approaching the ultimate speed limit of the universe. At such speeds, distance collapses and time behaves strangely. But those consequences can wait. What matters here is the impression. This is not light passively radiating into space. This is matter being thrown outward with intent-like precision. The effect is deeply unsettling because it contradicts a long-held assumption about how power should appear in nature. We expect powerful events to be spherical, explosive, indiscriminate. When a bomb detonates, it expands in all directions. When a star explodes, it sends debris outward as a shell. Directionality feels artificial, engineered. And yet, here it is, written across intergalactic space. Two beams, perfectly opposed, unwavering across distances that dwarf anything humans have ever constructed. Before understanding how such structures form, it is important to feel what they imply. A galaxy, something composed of stars, dust, and empty space, has become capable of behaving like a machine. Not metaphorically, but functionally, it produces output. That output is constrained, focused, and delivered far from its source. This is the moment where the idea of the most powerful thing in the universe stops being about brightness and becomes about reach. Only after this image settles does explanation begin. The jets do not emerge randomly, and they do not erupt because the system is chaotic. They appear because the quasar is highly ordered in a very specific way. The accretion disk that surrounds the black hole is not only a source of heat and radiation, it is also a rotating structure with a clear axis. Everything in the disk moves around a common center, and that shared motion defines a direction that is different from all others. Within this geometry, there are only two paths that are not blocked by dense orbiting matter. Directly above and directly below the plane of rotation. Energy generated in the disk cannot escape sideways easily. The disk is thick with material, crowded, turbulent, resistant. Any attempt to move laterally is quickly absorbed, scattered, or converted back into heat. The polar regions, by contrast, are comparatively empty. They are the only directions where energy can move outward without immediately colliding with more matter. This asymmetry alone begins to shape the outcome. Power, when confined, does not spread evenly. It seeks the path of least resistance, and in the quasar, that path exists in only two directions. Magnetic fields quietly complete the picture. The disk is filled with charged particles, and charged particles in motion generate magnetic structure. As the disk rotates, these fields are twisted and wound, becoming stronger and more organized. Over time, they align with the system's axis, threading the space above and below the disk like invisible rails. Matter caught in these fields does not move freely. It is guided, constrained, and accelerated along the field lines, forced into narrow channels that resist spreading. This is how the jets take shape. Not as explosions, but as flows. Not as chaos, but as alignment. Energy that was once distributed across a wide, turbulent disk becomes compressed into two focused streams. Motion that once circulated becomes motion that escapes. At this point, analogy becomes unavoidable because the structure is too familiar to ignore. The jets function like the exhaust of a reaction engine, where energy generated internally must leave the system in a controlled way. The comparison is not poetic, it is structural. In both cases, energy builds up, pressure increases, and release occurs along specific channels. The difference is scale. The quasar's exhaust does not propel a vehicle. It reshapes space across millions of light years. Another comparison is equally instructive. The jets resemble a cosmic compass needle, rigidly aligned with an axis that cannot be seen directly, but can be inferred from the unwavering direction of the outflow. No matter how chaotic the surrounding galaxy appears, the jets remain faithful to that axis, carving straight paths through environments that would otherwise bend and scatter them. They reveal order embedded within apparent disorder. There is also a more organic image, one that feels almost uncomfortable in its intimacy. The galaxy appears to be breathing. Matter flows inward through the disk, energy builds, and then the system exhales through the jets, releasing what it cannot contain. This is not life, but it is process. It is circulation. It is a reminder that the universe does not merely exist, it operates. Here, the meaning of power sharpens again. Power is no longer just the ability to produce extreme conditions locally. It is the ability to impose those conditions elsewhere. The jets do not simply carry energy away, they deliver it. As they travel, they interact with the surrounding medium, heating gas, compressing clouds, stirring regions that would otherwise remain cold and quiet. Their influence extends far beyond the quasar itself, sometimes affecting star formation in distant regions, sometimes preventing it entirely. This reach is what elevates quasars above other energetic phenomena. Many events in the universe are violent. Few are influential over such vast scales for such long durations. A supernova releases enormous energy, but its influence fades relatively quickly. A gamma-ray burst is staggeringly intense, but fleeting. A quasar, through its jets, maintains pressure on its environment for millions of years. Its power is not a moment. It is a condition imposed on the cosmos. Importantly, this does not require intention, intelligence, or purpose. The universe does not decide to aim. It is constrained into aiming. Given rotation, magnetic structure, and an escape route, direction is not optional. It is inevitable. This inevitability is what makes the phenomenon so unsettling. The universe, when allowed to operate under extreme but lawful conditions, organizes itself into systems that look engineered, not because they are designed, but because design is what order looks like from the inside. At this stage, restraint remains important. Not every quasar launches equally dramatic jets. Not every black hole produces them at all. The strength and persistence of jets depend on details that science is still refining: the rate of matter inflow, the configuration of magnetic fields, the rotation of the central black hole. Small differences can lead to large outcomes. This sensitivity does not weaken the claim of power, it reinforces it. Power in complex systems is rarely uniform. What matters is that when the conditions align, the result is unmistakable. A galaxy ceases to be a passive collection of stars and becomes an active engine. Energy flows are organized, directional, and far-reaching. Influence is exerted not just through light, but through motion, pressure, and force applied across intergalactic distances. By now, the phrase "the most powerful thing in the universe" has acquired substance. It no longer refers to a number or a comparison, but to a capability. Quasars do not merely shine brighter than anything else we know. They act, they shape. They extend their reach beyond their own boundaries, imposing order on scales that make individual galaxies seem small. And perhaps most unsettling of all, they do this without breaking any rules. The same gravity that pulls an apple to the ground powers these jets. The same electromagnetic laws that govern a compass needle guide matter across millions of light years. The universe does not invent new physics to create its greatest displays of power. It simply allows familiar laws to operate without interference. The result is a cosmos that is anything but static. Galaxies are not quiet islands. They are participants in larger flows of energy and influence. Quasars, through their jets, make this participation visible. They show that under the right conditions, a galaxy can become something else entirely. Not just a place where stars live and die, but a machine that works, processes, and reaches outward with sustained force. In the next layer, this outward reach will collide with its consequences. Power, once exerted, does not disappear. It reshapes what comes after. To understand why quasars mattered so much in the early universe, and why their influence still echoes today, we must now ask what happens when this directed power encounters the fragile process of making stars and building galaxies. But for now, it is enough to sit with the image. Two immense beams, launched from the heart of a galaxy, racing outward across cosmic emptiness, carrying with them the signature of the most powerful sustained engine the universe has ever revealed. The universe is not quiet, it is operational. There is a point at which comparison stops being a rhetorical tool and becomes a necessity, because the scale involved refuses to fit inside ordinary language. Quasars reach that point quickly, not because they are strange, but because they force the human mind to hold two incompatible truths at the same time and accept that both are real. One truth is size, the other is output. Individually, each can be managed. Together, they form a contradiction that reshapes intuition. Consider brightness first, because it is the most immediate measure of power the universe offers. A typical galaxy like the Milky Way contains on the order of 100 billion stars. Each of those stars is a furnace, steadily converting mass into light over millions or billions of years. Together, they form a diffuse glow that defines the galaxy's presence in the cosmos. Now, imagine a single region at the center of a distant galaxy, no larger than the scale of a planetary system, producing more light than all of those stars combined. Not briefly, not in a flash, but continuously, year after year, for spans of time long enough to shape cosmic history. This is not a metaphor, this is what observations show. To make this less abstract, it helps to change perspective. Picture standing in a city at night, every building lit, every street lamp glowing, every window shining. Now, imagine one single room somewhere in that city, glowing so brightly that it drowns out all the rest. Not because it is larger, but because it is converting energy far more efficiently. That is the relationship between a quasar and its host galaxy. The city does not vanish, the room simply dominates perception. Yet brightness alone does not explain why quasars are considered uniquely powerful. Power is not only about how much light is produced, but about how concentrated that production is. The luminous region of a quasar is astonishingly compact. While a galaxy may span 100,000 light-years, the central engine of a quasar operates on scales comparable to the orbit of planets. In some cases, the region responsible for the bulk of the emission could fit comfortably inside the boundaries of our solar system. To compress the output of an entire galaxy into such a small volume is not just impressive, it is unprecedented in sustained astrophysical phenomena. This compression is what forces the mind to slow down, rather than recoil. If the brightness were spread out, it would feel less offensive to intuition. Galaxies are large things can be bright. But here, brightness is packed tightly, like pressure building behind a dam. The system does not merely shine, it concentrates influence into a region so small that its surroundings cannot ignore it. The numbers involved often sound theatrical, but they are quietly precise. Some quasars release energy at rates equivalent to millions of suns shining at once. Not over a lifetime, but every second. To appreciate this, imagine replacing the sun with 1,000,000 identical stars and compressing them into a single point of light, without increasing the physical size of the source. That is the scale of output we are discussing. And again, this is not a rare anomaly pulled from the extremes of observation. It is a common property of luminous quasars, measured across cosmic distances and confirmed repeatedly. What prevents this from becoming overwhelming is the realization that this power does not come from destruction in the usual sense. Nothing is being blown apart. No galaxy is exploding from within. The host galaxy often survives the quasar phase, altered but intact. The power is exerted through persistence rather than violence. The quasar does not shout once and fall silent. It speaks continuously, imposing its presence through duration. This endurance matters. A supernova can briefly outshine an entire galaxy, but it fades within weeks or months. A gamma ray burst can release more energy in seconds than the sun will produce in its entire lifetime, but it is gone almost immediately. Quasars occupy a different category. They maintain extreme output for millions, sometimes hundreds of millions of years. Their power is not a spike, it is a plateau. At this point, the phrase "most powerful" acquires clarity. It does not mean the most energetic instant. It means the most influential sustained process we know. Quasars combine high output with long duration and tight concentration, a combination that allows them to overwhelm their environments rather than merely disturb them. This overwhelming effect is not limited to light. Radiation streaming from the quasar interacts with gas throughout the host galaxy, heating it, ionizing it, and in some cases preventing it from cooling enough to form new stars. The galaxy becomes aware of its center. Star formation slows or halts, not because stars are destroyed, but because the conditions required to make them are disrupted. The quasar does not need to touch anything directly. Its influence propagates outward through energy alone. Here, another misconception is corrected. It is tempting to treat quasars as freak occurrences, rare monsters that appear only under exotic conditions. Observations tell a different story. When we look far enough back in time, quasars are not exceptional. They are common. In the young universe, when galaxies were smaller, richer in gas, and more prone to collision, quasar phases appear to have been a normal stage of galactic evolution. Many, perhaps most, large galaxies likely experienced periods when their centers shone with quasar-level intensity. This means the universe once looked very different from what we see today. Galaxies were not quiet assemblies of stars. They were punctuated by brilliant cores, each exerting disproportionate influence on its surroundings. The dominance of quasars in the early universe is not an accident. It is a consequence of abundant fuel and unsettled structure. Power emerged wherever conditions allowed it. Understanding this reframes the idea of exceptionality. Quasars are not rare because they are difficult to produce. They are rare today because the universe has aged, gas has been consumed, structures have stabilized. The conditions that favor sustained central dominance have become less common. The quasar is not a miracle. It is a phase that the cosmos has largely outgrown. This perspective removes the last hint of spectacle and replaces it with inevitability. Given enough matter, enough motion, and enough time, a galaxy will produce something that overwhelms it, not because it intends to, but because gravity, allowed to operate deeply and continuously, leads there naturally. What makes this unsettling is how little novelty is required. There is no exotic ingredient that distinguishes quasars from ordinary cosmic processes. The same matter that forms stars fuels them. The same gravity that binds galaxies powers them. The difference lies only in concentration and access. When matter is allowed to fall far enough, fast enough, and continuously enough, the result outpaces every other known astrophysical process in sustained output. At this stage, the listener is not meant to feel astonishment alone, but acceptance. The numbers no longer need to shock. They begin to feel consistent, even expected. Of course, something that converts mass into energy more efficiently than stars, concentrates that conversion into a tiny region, and maintains it over millions of years would dominate its surroundings. Of course, it would overwhelm a galaxy built from slower, more distributed processes. The surprise fades, replaced by a quieter recognition. This is what power looks like when the universe is allowed to express it fully. And this is the crucial point. Quasars are not powerful because they are violent. They are powerful because they are patient. They apply pressure steadily, relentlessly, without pause. Their influence accumulates. Over time, that accumulation reshapes galaxies, alters histories, and leaves marks that persist long after the quasar itself has faded. This is why they matter, not as curiosities, not as distant spectacles, but as reminders that the universe is capable of sustaining extremes without breaking. That power does not always announce itself through catastrophe. Sometimes it simply outlasts everything else. With this realization, the first peak is reached. The idea of the most powerful thing in the universe is no longer a slogan. It is a description rooted in scale, efficiency, duration, and influence. What remains now is to understand what happens after such power is exercised, how galaxies respond, adapt, and survive, and what role these engines played in shaping the universe we inherited. That question leads not outward, but inward, toward consequences rather than mechanisms, and toward a universe that is quieter today, precisely because it once burned so intensely. To understand why quasars matter so deeply, it is not enough to measure their brightness or marvel at their reach. One must place them in time. Power in the universe does not exist in a vacuum. It appears where conditions allow it, and those conditions were radically different in the universe's youth. When we look far enough back, quasars stop looking like rare extremes and begin to resemble a dominant phase, a common expression of how the young cosmos behaved before it learned restraint. The early universe was not gentle. It was not quiet. It was not stable. Galaxies were smaller, less organized, and far richer in raw material than they are today. Vast reservoirs of cold gas filled interstellar space, waiting not only to form stars, but to be moved, disturbed, and redirected. Structures that now seem settled were then fluid, constantly reshaped by gravity acting across shorter distances and higher densities. In that environment, calm was the exception, not the rule. Collisions between galaxies were frequent, not the dramatic crashes of solid objects, but slow, inevitable interpenetrations where gravitational tides tore at structure and redirected motion. When two young galaxies passed close to one another, their stars mostly slipped by without contact, but their gas did not. Clouds were compressed, stretched, and driven inward. Angular, Momentum was redistributed. Material that once orbited peacefully at large radii found itself losing support and spiraling toward the center. Every such encounter fed the central black hole. This is the first reason quasars were more common in the past. Fuel was everywhere. Gas had not yet been locked away in long-lived stars. It flowed freely, responding quickly to disturbance. Central regions of galaxies were continuously replenished, allowing accretion disks to remain thick, active, and luminous for extended periods. The quasar phase was not a brief accident. It was a natural outcome of abundance. The second reason lies in structure. Young galaxies had not yet developed the stable, rotating disks we see today. Their internal motions were chaotic, their shapes irregular. This lack of order made it easier for matter to lose angular momentum and fall inward. In mature galaxies, rotation acts as a kind of support, keeping gas in wide orbits. In young galaxies, that support was weak or inconsistent. Matter fell toward the center more readily, and when it did, the quasar ignited. The third reason follows naturally. Black holes were being fed continuously. Not sporadically, not reluctantly, but persistently. The environment of the early universe ensured that once a quasar turned on, it often stayed on. The system was not allowed to relax. Fuel kept arriving, power kept flowing. Seen this way, quasars were not anomalies scattered across cosmic history. They were part of the universe's adolescence, a phase characterized by excess, instability, and intensity. The same way young stars burn brighter and faster than their older counterparts, young galaxies express their energy through quasars. This realization reframes the idea of violence. The early universe was not violent in the sense of destruction for its own sake. It was violent in the sense of inefficiency. Too much fuel, too much motion, too little regulation. Quasars emerged as a consequence of that imbalance, and here, the nature of their power becomes more subtle and more unsettling. Power is often imagined as something that creates. Quasars are powerful not because they create stars, but because they can prevent them. Their influence is not additive, it is regulatory. They do not build galaxies. They teach galaxies how to stop growing recklessly. As a quasar shines, it floods its host galaxy with radiation. Gas that might otherwise cool and collapse into new stars is heated instead, kept diffuse, ionized, and uncooperative. In some cases, powerful outflows driven by the quasar physically expel gas from the central regions, removing the raw material of star formation entirely. The galaxy does not explode, it starves. This is not destruction in the dramatic sense. It is discipline. A useful comparison is a vehicle with an engine that is too powerful for its frame. Without control, acceleration becomes instability. Steering becomes difficult. Growth becomes dangerous. The engine must be regulated, or the system fails. Quasars play a similar role on galactic scales. Their power forces the galaxy to slow down, to stabilize, to transition from chaotic growth to structured evolution. Another comparison is fire. A small, controlled flame cooks food and provides warmth. A fire that grows too large consumes its own fuel too quickly, leaving nothing behind. In the early universe, galaxies were piles of dry wood. Quasars were the blaze that burned through excess material, ensuring that what remained could settle into longer-lived forms. This regulatory role is one of the clearest demonstrations of why quasars deserve the title of the most powerful sustained phenomena in the universe. They do not merely overwhelm their galaxies temporarily, they shape their long-term fate. A galaxy that experiences a powerful quasar phase will form fewer stars afterward. Its structure will be altered, its future will diverge from galaxies that remained quiet. Importantly, this process appears to be widespread. Observations suggest a strong connection between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the mass and motion of its stars. This correlation implies coevolution. The black hole and the galaxy grow together, and quasars are the mechanism through which that growth is synchronized. This is not coincidence, it is feedback. The quasar does not simply feed on the galaxy, it responds to it. When gas flows inward too efficiently, the quasar ignites and pushes back. When gas becomes scarce, the quasar fades, allowing the galaxy to resume quieter star formation. The system oscillates, not wildly but within bounds set by gravity and energy balance. Power becomes a stabilizing force rather than a destructive one. This is perhaps the most counterintuitive aspect of quasars. They are extreme, but they are not reckless. They impose limits. They prevent runaway behavior. They are violent only in the way adolescence is violent, intense, unstable, but ultimately formative. As the universe aged, these regulatory episodes became less frequent. Gas reservoirs diminished. Galaxies grew larger and more ordered. Collisions became rarer. The conditions that fed quasars naturally declined. The universe did not lose the ability to create quasars. It lost the need. Today, quasars are uncommon because the universe has matured. Power is still present, but it is distributed differently. Star formation proceeds at a slower pace. Black holes accrete more quietly. The cosmos has learned restraint, and quasars are the scars of that learning. Seen from this perspective, quasars are not simply powerful objects embedded in galaxies. They are historical agents. They mark the transition from a young, chaotic universe to a calmer, more structured one. Their power lies not only in what they emit, but in what they prevent, in the futures they redirect. This reframing removes any lingering sense of spectacle. Quasars are no longer cosmic fireworks meant to impress distant observers. They are functional components of cosmic evolution, enforcing balance through excess. Their power is systemic, not theatrical. And yet, humility remains essential. While the broad outlines of this story are supported by observation and theory, details are still debated. The exact mechanisms by which quasars heat or expel gas, the timescales over which regulation occurs, the degree to which every large galaxy experienced a quasar phase. These questions are active areas of research. The universe has left clues, not blueprints. What remains clear is the pattern. Where the universe was young and overabundant, quasars flourished. Where quasars flourished, galaxies were forced to mature. The most powerful sustained engines in the universe were not merely expressions of excess energy, they were instruments of transition. This realization carries a quiet weight. It suggests that power, at the largest scales, is not about domination, but about shaping trajectories. Quasars did not rule the universe forever. They burned intensely, taught their lessons, and faded, leaving behind galaxies that could persist in a quieter cosmos. In the next, the story will turn inward again, away from history and toward perspective. Having seen how quasars shaped the universe's youth, the question becomes more intimate. What does it mean for us, here and now, to exist in a universe that once allowed such extremes and still carries their imprint in its structure and silence? But for now, it is enough to recognize that the universe's most powerful phenomena were not accidents. They were phases, and in their violence, they taught the cosmos how to grow up. Quasars shine brighter than galaxies, shape their hosts, regulate star formation, and dominate the early universe with sustained influence. They seem to justify the phrase, the most powerful thing the universe has ever built. And yet, this is precisely the moment where science insists on slowing down. Not because the picture is wrong, but because it is incomplete. Power, when understood honestly, reveals not only what we know, but also the edges where knowledge thins and humility becomes necessary. Despite decades of observation and increasingly sophisticated models, quasars remain, in important ways, unpredictable. We know what they can do, but we do not fully understand how they decide when to do it. One of the most basic questions still resists a clean answer. How does a quasar turn on, and how does it turn off? At first glance, the question sounds simple. A quasar shines when matter falls into its central system, and it fades when that supply runs out. But reality refuses to stay that neat. Observations show quasars flickering on timescales far shorter than entire galaxies could reorganize. Some appear to dim dramatically, even vanish, over periods that are short by cosmic standards. Others remain active far longer than simple fuel, estimates would suggest. The connection between available matter and visible activity is real, but it is not direct. Something in the system mediates, delays, or interrupts the flow. This uncertainty is not a failure of measurement. It is a reflection of complexity. Accretion disks are turbulent, magnetized, and non-linear. Small changes in structure can lead to large changes in output. A slight rearrangement of magnetic fields may choke off a jet. A shift in disk thickness may trap radiation longer or release it faster. These systems are not switches with clean positions. They are evolving environments, sensitive to conditions we cannot yet fully observe. This leads to another puzzle that challenges intuition: the existence of quiet quasars, objects that, by mass and environment, seem capable of extraordinary output, yet remain subdued. Some supermassive black holes sit at the centers of gas-rich galaxies and still show little activity. Others produce bright disks, but weak or absent jets. If quasars are the natural outcome of mass and motion, why do some systems hesitate? The answer, for now, is that nature allows multiple solutions. The universe does not maximize output simply because it can. Geometry matters, history matters, alignment matters. A black hole's rotation, the orientation of inflowing matter, the configuration of magnetic fields, and the timing of galactic events all shape what is possible. Two systems that look similar from afar may differ in crucial internal details, leading one to blaze and the other to whisper. Even the black hole itself, the silent anchor of all this power, resists full understanding. We know that most large galaxies host them. We know they grew rapidly in the early universe, but we do not yet know precisely how the first ones formed so quickly, nor how their growth synchronized so closely with their host galaxies. The relationship is undeniable, but the causal chain remains under construction. This brings us to a deeper admission. Our models are provisional. They are not lies, but they are not final truths either. Simulations capture fragments of reality, not the whole. Observations are filtered through distance, time, and limited instruments. Every diagram of a quasar is a simplification, a carefully chosen slice through a system that is richer and more complicated than any single representation can convey. The temptation, when confronted with something as powerful as a quasar, is to assume that understanding power means mastering it conceptually. That once we name the mechanisms, the mystery dissolves. Science teaches the opposite lesson. The more powerful the phenomenon, the more it reveals the limits of our grasp. Not because the universe is hiding, but because it is under no obligation to be simple. This is where the idea of power subtly shifts. Quasars are powerful not because they are omnipotent, but because they operate without regard for human categories. They do not care whether we understand them. They do not adjust their behavior to fit our models. They simply follow the laws of physics as those laws unfold at extreme scales. Their indifference is part of their authority. Recognizing this indifference is not discouraging. It is clarifying. It reminds us that science is not a conquest, but a conversation. We do not force answers from the universe. We listen for patterns, test hypotheses, and revise our understanding when reality disagrees. Each unanswered question about quasars is not a gap to be embarrassed by, but a boundary marker showing how far careful reasoning has carried us so far. Even the phrase, "the most powerful thing in the universe," benefits from this restraint. It is a useful description, not a final verdict. There may be phenomena we have not yet observed, processes operating under conditions we have not yet imagined. The universe has surprised us before. It will do so again. Power is contextual, and our context is limited by what we can see. What quasars offer, then, is not a sense of dominance, but a lesson in scale and patience. They show that immense power can exist without chaos, that regulation can arise from excess, and that influence does not require intention. At the same time, they remind us that understanding such systems fully may take generations, or may never be complete in the way we intuitively desire. There is a quiet dignity in this realization. Knowledge is not diminished by admitting uncertainty. It is strengthened. To say we do not yet know is not to retreat, but to stand honestly at the edge of understanding. In a universe where quasars can overwhelm galaxies, the most human response is not arrogance, but attentiveness. In this sense, science mirrors the very systems it studies. Just as quasars regulate their galaxies by responding to excess, scientific understanding regulates itself by responding to evidence. It advances when data flows, pauses when models strain, and adapts when assumptions fail. There is power in this restraint, a different kind from the one that lights up the cosmos, but no less important. After traveling through structures capable of outshining galaxies and reshaping cosmic history, the mind naturally looks for a place to stand. Not to retreat from the scale just encountered, but to situate itself honestly within it. This is not a philosophical move, but a spatial one. Where are we exactly in a universe that once allowed such extremes and still carries their light across distances so vast that time itself becomes visible? The light from a quasar does not arrive quickly. It does not hurry. It begins its journey when the universe is young, when galaxies are unstable and black holes are being fed relentlessly. It moves outward at the fastest speed nature allows, yet still requires billions of years to cross the expanding fabric of space. During that time, stars are born and die, planets form and erode, civilizations rise and vanish. Entire histories unfold beneath a beam of light that does not notice them. When that light finally reaches Earth, it does not announce itself as ancient. It appears simply as a point in the sky, a faint glow that requires careful instruments and patient observation to distinguish from ordinary stars. There is nothing in its appearance that conveys the violence of its origin or the scale of its journey. To see it at all, one must be still, attentive, willing to listen rather than expect spectacle. This is the first quiet correction quasars offer us. They remind us that power does not always arrive loudly. The most influential phenomena in the universe do not seek attention. They persist, indifferent to whether they are witnessed or understood. Their light reaches us not because we are important, but because we happen to exist along its path. In this sense, observing a quasar is an act of coincidence rather than privilege. We are not at the center of the story. We are at the edge of its afterimage. Distance deepens this realization. In everyday life, far means diminished, less relevant, less real. In cosmology, far means old. The farther away we look, the further back in time we see. A quasar observed across billions of light years is not just distant. It is a record of an earlier universe, preserved in transit. Its light carries information not only about where it came from, but about when. This inversion of intuition is difficult to absorb fully. To look outward is to look backward. To study quasars is to study a time when the universe was fundamentally different, when its most powerful engines were active, common, and transformative. What we see is not how the universe behaves now, but how it behaved when it was young and unrestrained. And yet, this ancient light arrives here, now, entering human instruments, human eyes, human understanding. The gap between its origin and its reception is filled with silence. The universe does not update us on what has changed since the light left. It does not provide context or reassurance. It simply delivers what it has carried all along. This indifference is not hostility, it is scale. Quasars do not care that we exist. They did not shine for us. Their power was exerted long before Earth formed, long before life learned to observe. And yet, here we are, capable of reconstructing their story, not because the universe intended it, but because its laws are consistent enough to be read. This consistency is where meaning quietly emerges, without being imposed. The same physical principles that allowed quasars to dominate galaxies also allow us to understand them. Gravity curves space whether or not it is named. Light travels whether or not it is seen. Knowledge arises not from control, but from alignment with reality. This brings us to responsibility, though not in the moral sense usually implied. The responsibility here is one of proportion. To know that the universe can sustain engines powerful enough to overwhelm galaxies, yet remain indifferent to our existence, is to recognize that understanding is not a path to dominance. It does not grant authority over nature, it grants perspective. Quasars teach this lesson quietly. They show us that power exists on scales where human ambition becomes irrelevant. They show us that the universe once burned far more intensely than it does now, and that our calm epoch is not the default state of things, but a consequence of earlier excess. They remind us that stability is earned, not guaranteed. At the same time, they affirm something subtle but important. We are not central, but we are not excluded. The universe does not care whether we observe it, but it allows observation. It does not simplify itself for our comfort, but it leaves traces that can be followed. The fact that we can reconstruct the life cycle of quasars at all is not a triumph over nature, but a collaboration with it. To listen to a story like this, lying still, letting the scale wash over the mind, is itself an act of alignment. The body rests. The universe speaks in light that has traveled longer than any human memory. There is no demand to react, to judge, or to conclude, only to notice. In this quiet noticing, the phrase, "the most powerful thing in the universe," takes on its final nuance. Power is not something that exists to be confronted or overcome. It is something that exists regardless. Our role is not to challenge it, but to understand where we stand in relation to it. We are not the center, we are not the cause, but we are witnesses. And in a universe that does not care, witnessing is not insignificant. It is the only way scale becomes meaning and distance becomes history. If the universe is capable of building engines that outshine entire galaxies, systems so powerful they once shaped the fate of cosmic history, then it is natural for the mind to wander toward a quieter question. Not one that demands an answer, but one that lingers gently. What place does this small, listening awareness occupy in a cosmos that can burn so intensely and yet remain indifferent to who is watching? Somewhere far beyond this moment, the universe continues exactly as it always has, indifferent to whether it is noticed or named. The engines we spoke of tonight are mostly silent now, their work already woven into the structure of galaxies and the calm that followed. What remains is not their power, but the fact that such power once existed at all. And here, in this brief pause, there is a mind capable of noticing that fact without needing to control it. Perhaps that is enough. If you find comfort in listening as the universe is explored slowly, without urgency or demand, you may remain here and let the night continue.